Welcome everybody to our next Solar Climate Intervention Virtual Symposium. And today we have two speakers, Temitope Egbebiyi and Walker Lee. So we start with Temitope, who is a postdoctoral research fellow at the Climate System Analysis Group, Department of Environmental and Geological Science, University of Cape Town in South Africa. And he will today talk about the impact of solar aerosol geoengineering on crop sustainability in sub-Saharan Africa. Okay, please go ahead. The floor is yours.
Good afternoon, everyone, and thanks for having me. My name is Temitope Egbebiyi. I'm at South Africa, and I'm working at the Climate System Analysis Group. So this afternoon, I'll be talking to us about the impact of SAI, stratospheric aerosol injection, on crop suitability in sub-Saharan Africa, then with a focus on West Africa. So basically, what informed this study is because of the critical impact that agricultural production is to our economy in sub-Saharan Africa, contribute up to 15% of the GDP into the region, and then it's one of the means of livelihood for many countries in sub-Saharan Africa. And as a result of that, the aspect of ensuring food security, as mentioned in the SDG goal, is one of the key things that different countries in the region have been looking at. So one of the ways that we need to understand that is by looking at where to cultivate our crops, where the crops we are growing now, what are the things. Studies have shown that some crops will not be suitable in some areas, some crops that are not suitable in some places now will become suitable in other regions. But unfortunately, there have been little or no study on that using looking at climate geoengineering, and that is one of the things that informed this study. And crop suitability is basically defined as a function of a specific location, climate condition, how it meets the requirement for cultivating a particular crop in that particular area. And this is very important because it enhances planning, agricultural planning, and then for different regions and countries. It helps to identify, helps with adaptation strategies in the region, and then helps to provide alternative location for crop production, like I mentioned before, where we can grow some crops now, what are the areas where we can go. So these are kind of things that can help us. Also because of changes in temperature with the warming may lead to drought conditions, as some studies have shown, and last IPCC report to mention that. And then with decrease in future rainfall in some part of the region too, there are threats to cropland suitability, and that can lead to crop failure. So that's why this particular talk is important. And in terms of research, like I mentioned, few studies on cropland suitability in Sub-Saharan Africa. A lot of people have looked at that under RCP 8.5 and even the SS3 now, but there's still lack of knowledge in terms of what are we going to do. And most of the studies too that have been done with SAI in Sub-Saharan Africa has been on climate extremes, looking at different variables like temperature, rainfall, what will happen to wind. But in terms of impact modeling, there are still few studies on that. So that's what informed this particular work. And in terms of the climate variables used, we use for the historical periods from 1980 to 2009, and then for the years we use 2060 to 2089, RCP 8.5. And the solar the GLENS experiment is the major experiment that we use for this one. Sorry, I think I missed that there. And then for the variables that is needed for our crop suitability model is monthly minimum temperature, mean temperature, and then total monthly rainfall. And this out talking to us about there are different crops that we try to look at, but basically look at cereal, which is maize, legumes, cowpea, and then root and tuber cassava. These three were chosen because of their key importance to the region among other crops, because maize is a stable crop, cassava too is very prominent, like we'll see in some part of the region like West Africa, which can be processed into different crop, into different use for people in their homes. So before doing this particular work, the data were bias corrected using the 12-day crude data set, which has been widely used in terms of impact modeling. And then the bias corrected output was what was used that was fed into EcoCorp, which is a cross-suitability model developed by FAO, which basically to compute shows you where optimal, suboptimal, and non-optimal condition to evaluate relative suitability of crops in response to climate variation or climate variables like temperature, rainfall, and sometimes look at the growing season. And basically, it's a statistical model. What it does is that it takes the total suitability is what we analyze, and that is a product of the suitability in terms of rainfall and temperature, which I will show only in the next slide. And that suitability index comes either from 0 to 1, or you can put it in percentage from 0 to 100%, where over 0 means area that is not suitable, and 1 means this area is very, very highly suitable. So this is the based on the data set that we use from the Glens experiment. And then this is just from, this is the crop suitability threshold for the crop model that were used. Sorry, it's showing 8 crops there. I just put this one out. This is the one I'm using now for this study, but with other crops that we have used, you see temperature there in terms of team talking about minimum temperature, the optimum minimum temperature that is needed, the optimum maximum temperature, and then the maximum temperature, in the sense that, so for example, the maximum temperature is any temperature above that, the crop will not be able to grow. The same thing for the minimum temperature below this will not be suitable for the crop. And we have the same thing too as well for rainfall. So this is just a schematic diagram showing eco crop, where you have the optimum condition there, then where it's marginal, and then with way in the area where you be, that it shows you that it will not be suitable for the crop. And this is just to show the three-dimensional diagram showing the suitability with regards to eco crop, as shown by Ramirez. So basically, before we look at the impact, just look at generally over the region, the impact of the variables we want to use, just to look at them. And then in the historical period, here is showing for us total monthly rainfall, mean temperature, and minimum temperature over Africa. We see with global warming, we notice that temperature is increasing over the region. But by the time we introduce the SAI, we see that it lowers the temperature. However, it affects rainfall too. In the area, in some places like East Africa has been reflected most of the IPC reports and some findings that become wetter, but with the introduction of SAI, based on this experiment at the moment, showing that there might be drying over the region, and some other places too might be affected. So having seen that, we want to see how that will affect this crop over the region. So this is the 3 crops that I mentioned, which at some point now I will center it down to West African region, but generally over sub-Saharan Africa, we see here, like I mentioned, underneath here is the suitability index from 0 to 1, between 0 to 0.2 means it's not suitable, very marginal between 0.21 to 0.40, and highly suitable anything above 0.81. And generally, we can see here that in terms of historical period, where the crops are grown in West Africa, in sub-Saharan Africa, basically in southern part of the region, especially the south eastern part, we see that we can't see the crops being that suitable with what we have from our models. But you see in the other part of the region like West Africa, Central Africa, and then some part of East Africa, the suitability of some of the 3 crops that we're looking at. Then looking at the impact of global warming on the crop, most areas there are no changes, but we see area where we see that there will be changes in terms of the suitability growth in some part of East Africa, majorly. Then some part of West Africa, Central Africa shows that there may be decrease in terms of suitability for the crops in terms of maize. For cowpea, majorly no changes, but we see most of that there may be increase in suitability with cowpea in Eastern Africa part. Then over for cassava, in West Africa, we notice that there may be decrease in terms of growing cassava. Some part of East Africa is showing a bit of increase, and then in the upper part of Southern Africa and the southern part of Central Africa, you can see a kind of an increase there. But the reverse is the case with what we have with SAI, where we see that things might decrease. We see an increase in suitability with SAI. So the fourth column here is showing the difference between what we have between SAI and global warming. That's the difference between the aerosol injection and what we have with RC.5, RCP 8.5. That is what we have in the fourth column. This is talking about in terms of growing month suitability in terms of planting season. So here it's showing us the first month of the best 3 months for the seasonal crop, and then cassava to showing us for the terms of the planting for the different crops. Historical period is what we have in the first column. With climate change, you see that there may be an early planting for maize in Oluwa, West Africa, and some part of extending to some East African part, or some part of Central Africa towards the east, showing that there may be delayed planting. Not much change with cowpea. Then with cassava, we see a kind of a mix there too, showing the early planting, because where the arrow that shows brown here is showing decrease, that early planting, where the late season will be the one that is showing us the purple color. So where in Central Africa showing that there will be the late season for about a month or 2. But with SAI, the reverse is the case, where they are expecting global warming impact causing a delayed planting. We might likely have a kind of early planting there in those regions for Central Africa, and then in West Africa for both cassava and maize, showing that there will be late season for the crops. Having seen that, then narrowing that to West Africa, just like I've shown in terms of suitability there, then just to look at things, narrowing down to that, because I will still look at the other region in subsequent, maybe prediction possible. But looking at West Africa, because of the key tool to the region among other parts of sub-Saharan Africa, we see the changes that cassava will be more in terms of global warming, is going to be affected in terms of the suitability growing. But going back with SAI, is showing that there will be increase in terms of suitability, be favorable in terms of growing cassava in the region. Why the reverse is not for maize too, you notice that in the other part where there's projected decrease in suitability, maize too, there's a kind of projected increase for maize over the region with the impact of with injection of aerosol injection into the stratosphere. Why for cowpea the reverse is the case in terms of the suitability. The same then for the growing month too, just the same similar pattern, even though we may have early planting with impact of warming, but Esther is saying that there may be delay season in terms of cultivating the crop. Why for cowpea we have an early planting for growing maize, cowpea, and cassava. So this shows just some bar chart of the percentage grid point of distribution for maize and cassava over West Africa, like just to show an overview of what we have seen from the plot there. Then just to narrow it down because of time, bringing it to country, how does it apply to different countries? So this is a bar chart for the different country in West Africa, and then so the orange is for the greenhouse gases, the blue is for the present day, and the green is for SAI. Compare it to across different countries to see how it affects different crops. We can see for maize, there's kind of a varied impact of SAI over different crops being cultivated in those regions, but basically we can see that it will improve the suitability of maize in about 50% of the countries in Africa. Notice that for Liberia, you see that in Togo, for Sierra Leone, Ivory Coast will be impacted, Guinea, and then so in those countries, use the SAI application will be favorable for some of them in planting maize. Why in some parts too, you see that like Nigeria and Nigeria basically see that the impact of the global warming is still going to affect terms of suitability of growing crops. For cowpea, you see that basically there is the impact of global warming is more dominant in terms of different countries and the effect on the suitability of growing those crops, even though there's the impact of pesticides don't really make a difference in terms of the area to cultivate those crops. But for cassava, we see the impact here more, that in most countries, it's going to really improve the suitability of some of the crops with looking at compared to the impact of global warming. That's what I mean by efficient output of SAG relative to global warming and comparing to the historical period. However, that doesn't mean that will take us to what we have in the historical period, but at least for cassava is a bit better. It improves suitability compared to what we can observe from the historical period, the issue of aerosol injection. Basically, so in the conclusion, just to say that the intervention may reduce the magnitude of decrease in suitability for maize and cowpea, while that of cassava is yet to increase over the region, especially in West Africa. But for cowpea, SA intervention may enhance suitability of maize and cassava cultivation in most part of the region, and as we've seen with South Africa, with West Africa, but relative to, except for cowpea, we see that it's totally different from what we saw with cassava and maize. And then to notice that there will be this season for cassava, I think maize in West Africa, while we expect early season for maize in the region. However, like I said, this is based on the CSM1 congruence experiment. So now that we have other data that we are working on now to compare these results before we can make an informed decision and then give us a robust output. But nevertheless, this has given us a kind of a foretaste of what we can expect with a climate geoengineering intervention on cropland suitability over the region. Thank you.
Thank you very much. Very nice and nicely stayed on time.
I can't hear you. Can you hear me?
Yes, we hear you. Do you hear me?
Can you hear me?
Yeah, we hear you. But okay. Maybe if you can't hear us, we may have to put questions in the chat. Do you hear us now?
Yes, I can hear you. Sorry.
Oh, good.
I can hear you perfectly now.
Okay, so are there any questions? If so, please indicate it by raising your hand, or you can type something in the chat. I see your hand, Mike. Is that you want to ask a question? You have to unmute.
Yes, if I could.
Yes, please.
So it looks like it was mainly related to changes in precipitation, which is interesting. But when I looked at the various indications of agreement among models, there weren't many plus signs around. So I guess what I'm wondering is, how do the changes related to precipitation that you saw over the average compare to variability that occurs year to year?
Hello, please, can you come up again, please? I didn't get your question. Can you repeat the question, please, Mike?
Yeah, this is Mike.
Yeah, can you repeat the question? He couldn't get it quite right.
Well, I'm curious how much the changes in precipitation that you're seeing as a result of the climate change compare to the variability of year-to-year changes that cause successes and failures of crops.
Okay, thanks. So one of the things that we are just trying to look at with in terms of that is with what we find, just like you have observed, is to see which of those two variables is really driving the suitability of the crops in the region. We notice that yes, there will be changes in terms of precipitation, and West Sub-Saharan Africa is majorly rain-fed driven in terms of the suitability. But at the same time, we notice that SAI2 will lead to a bit of reduction in rainfall over the region. And then that might be one of the things that is impacting the suitability of some of those areas that we are seeing, especially for cowpea. Cassava has been observed that it's a bit a drought-resistant crop, so maybe that is why the challenge in terms of rainfall over the region might not really affect it. But it's one of the things that we are trying to look at now, putting temperature and then rainfall to see which of them is really impacting this with what we have found in these results. So I can't really give you an immediate answer. It's one of those things that we are looking at the moment too. Does that answer your question?
Yeah, yes, I mean, I think there's a lot of variability. And so I'm wondering if it would help to look at sort of year by year results rather than average changes over decades.
Yeah, I think he
Thanks.
said that he does see a reduction in rainfall in SAI in general. And so your suggestion is just to look more at the annual year-to-year variability as well. Okay.
Thanks, that's noted.
Okay. Let's go on to the next question by Hong Wei. Thanks for putting it in the chat, but you can also just repeat it here.
Okay, sure. Thanks for the great talk, Temitope. So my question, as shown in the chat, it seems like in your last several slides, the SAI can significantly increase crop suitability for Gabby's soil, this country. So I'm wondering, have you checked whether it's because SAI mainly influence temperature or precipitation to cause this suitability decrease?
Yeah, thanks, Son. So like I mentioned the previous one, so the impact we've seen from different countries, now having seen that. So what we are now doing is to look at it in terms of both the rainfall and temperature to see which one is really driving the suitability of the crops at those regions now, at different countries. So those are the things that we are trying to look at. And like Michael pointed out, after looking at that, maybe we may want to look at the changes within the years to see how that impacts across suitability before we can make an informed decision. But for now, I can't really pinpoint. If I tell you that it's the rainfall, and at the end we find the temperature, so those are things we are still trying to see which one affect different countries. Then we can be able to make informed. So it's still a work in progress. But thanks for the question.
Thank you.
Okay, is there another question? I would have a question too. Very, very nice talk also. So you said in your last slide, if I understood correctly, that the planting times would change with SAI, obviously, or maybe being earlier or later, depending on the crop. And that probably is the case for also climate change. Are you suggesting that farmers can adapt to either SAI and climate change the same way?
No,
when they change
that's not. No, I'm not implying that. So one thing we are trying to look at there is that in terms of some studies to have shown in terms of part of climate change that there may be changes in terms of the planting season or growing season. So what we just want to see in terms of SCI is that is it within the same period or which of them comes first? So like we've seen now, we've seen that with this one simulation runs, I've still seen the times of changes that is reverse to what we see in climate change. But like I mentioned, we are now looking at other experiments to be able to show before we can make an informed decision that, okay, this is what we can tell farmers in terms of when to plant. So it's still one of the things that we are trying to unpack now from this first analysis that we have done before we can boldly say, okay, with what we've seen with SAI, if for your cassava, you might have an early planting season, or for your cowpea, there might be delay season. Yeah.
Okay, thank you. Are there any other questions? Maybe you can stop sharing your screen, and if there aren't any more questions, we can move forward. And I give this for now to Matthew to continue. Thank you.
Yeah, thanks, Simone. So our next speaker is Walker Lee. Walker, do you want to stop sharing your screen?
Sure, I can do that. Oh, no, that's, I think I have to go into slideshow mode first, and then I can share that. How does this look?
Yeah, perfect. So
Awesome.
yeah, Walker is a PhD student at the Cornell University. I understand he has just defended his thesis So I wasn't sure whether to put Dr. Walker Lee or not on the website. Anyway, so he has done mostly work on stratospheric aerosol injection, but today he's going to talk about comparing SAI and marine cloud brightening. So go for it.
Thank you very much, Matthew. As Matthew mentioned, I'm just finishing up my PhD at Cornell, and most of my work has been on stratospheric aerosol injection. But last summer, Yaga and Jack over at NCAR asked if I could take a look at some of their marine cloud brightening simulations for the purpose of comparing with SAI and also just analyzing the surface climate impacts, especially at high latitudes in the Arctic, which looking at Arctic impacts of SAI was a big part of my dissertation. So I looked at that in marine cloud brightening simulations as well. For some context, I'm sure the vast majority of people here have seen this before. 3 different methods of reflecting sunlight identified by the National Academy's report that came out in 2021. So I'll be comparing stratospheric aerosol injection and marine cloud brightening. Just a quick overview of the differences between the two. SAI is where aerosols are injected into the middle atmosphere, and marine cloud brightening is where particles are injected into marine clouds to brighten them and reflect sunlight that way. SAI is analogous to volcanic eruptions, which cool the planet through a phenomenon that we call a volcanic winter. And MCB is analogous to ship tracks. If you've ever seen satellite photos of the ocean, you can sometimes see the paths of ships, and that's because aerosols or other particles from their smokestacks can brighten the clouds behind them, and MCB would aim to replicate this effect. SAI would be deployed at a relatively higher altitude, and as a result, the stratospheric circulation would carry the aerosols to have an effect on a large portion of the planet, if not all of it. And the reason that aerosols would go into the stratosphere and not the troposphere is because the stratospheric aerosols would have a much longer lifetime, on the order of a year or 2. In contrast, MCB would be deployed at a very low altitude, and because of that, the results would be much more local and short-lived than for SAI. The simulations that I'll be comparing for SAI, Yaga and Dan Visioni from our group at Cornell published some simulations that they're referring to as ARISE SAI, specifically ARISE SAI 1.5. I think ARISE stands for Assessing Responses and Impacts of Solar Geoengineering on the Earth System, and those results were published last year. The MCB simulations run by Jack and Yaga at NCAR have not yet been published. I understand that the writing up of the manuscript is in progress. And then we're not sure whether the stuff I'm talking about today would go in that paper or might go in another paper, or might just inform our understanding of marine cloud brightening for future simulations. So next, I'm going to talk a little bit about the design space. The design space is a really important concept in solar geoengineering, and it's the idea that different strategies produce different outcomes. By strategy, the main components of a solar geoengineering strategy are: what is the magnitude of the forcing and where are you applying it? So for example, for stratospheric aerosol injection, the first strategy a lot of people looked at would be to inject over the equator. However, because of a phenomenon called Arctic amplification, where the poles respond more strongly to global warming, SAI just over the equator has been found to overcool the tropics and undercool the poles in SAI simulations. And so to prevent this, you might consider injecting at multiple locations to try and cool the planet relatively evenly. And I'll be referring to this as a globally focused strategy. However, you could, if you wanted to try and cool one area of the planet preferentially. If you wanted to only focus on one or both of the poles, you could inject at, for example, 60 north, and we could call that an Arctic focus strategy. Additionally, how much you inject is important. You might decide, oh, no, I'm sorry, that's the next slide. Likewise, for local marine cloud brightening, you could deploy your marine cloud brightening over a very small region. For example, it's been theorized that marine cloud brightening could be deployed just by Australia to try and protect, to cool the waters around the Great Barrier Reef and protect that. Or you could try and do something similar where you try and cool large portions of the planet relatively evenly by deploying in multiple locations that would be susceptible to marine cloud brightening. Now, the way that this is implemented in CESN2 is that for SAI, SO2 is inserted into a grid box, and the assumption right now is that SO2 fills the grid box evenly. We know that's not physical, but the aerosol modules do a pretty good job of replicating Pinatubo. So for now, that's what we have to work with. And to vary the amount, we can simply add more SO2 into a single grid box. For marine cloud brightening, the way that Jack and Yaga implemented this in their simulations is for every grid box they chose to implement marine cloud brightening in, they artificially drove the cloud droplet number density up to 370 per cubic centimeter. And this was they considered this to be a reasonable threshold for how high they could get the brightness of the clouds. Now, unlike with SAI, where you can change the amount of SO2 in a single grid box, MCB is more in these simulations. MCB is considered a binary effect. It's either on or off. And so if you want to increase how much marine cloud brightening you're doing, you modify a larger area of the ocean. And this is important because for SAI, we have multiple degrees of freedom where you can choose which grid boxes you want to inject in. But for marine cloud brightening, at least in the simulations we have so far, there's only 1 degree of freedom right now. You don't necessarily get to choose which area of the ocean you're deploying in if you're restricting yourself to the most susceptible regions, as Jack and Yaga did. Your only degree of freedom is then to modify a larger or smaller area of the ocean. One way that you could go about a solar geoengineering strategy is by implementing a constant amount of intervention. For example, a number of teragrams of SO2 that stays constant over time with the injection rate per year is constant, or modifying a constant % of the ocean surface in the case of marine cloud brightening. However, global warming is not expected to be a constant scalar. It's expected to increase with time. And so you could also design a solar geoengineering strategy that increases linearly with time by increasing steadily increasing your injection rate or increasing the area of the ocean that you modify. You could even go a step further than this. Your initial estimate for how much you need to increase your intervention with time might be imperfect, and you can employ some kind of feedback algorithm that would adjust the scope of your intervention over time in order to drive the climate towards some desired outcome, such as a constant global mean temperature. The simulations that I'll be looking at today were designed to have at least some similarities for ease of comparison. They both use version 2 of the Community Earth System model. They branch from the SSP 2.4.5 background, which is a middle of the road moderate warming scenario. The branch begins in the year 2035 and runs until 2070. Unfortunately, we have 2 different versions of the same climate model, or specifically the atmospheric component. SAI needs to use WACCM, the whole atmosphere community climate model, because we want to capture the dynamics of the stratosphere. Whereas the MCB simulation used CAM, just the regular old community atmosphere model, because it's much, much cheaper than running WACCM. So we are going to have 2 different baselines to compare to. SAI uses the global strategy where they're trying to cool the planet relatively evenly. MCB also intends to use a global strategy, but there's a little asterisk next to this interpretation, and I'm going to touch on that briefly in a moment, because remember that if we're restricting ourselves to the most susceptible areas of the ocean, we don't get to choose exactly. That is a way of choosing our locations for us, and it turns out if you're only doing a small % of the Earth's surface, those are all in the same place. The SAI simulations are feedback regulated. The goal is we chose a global mean temperature target that were defined. It was defined as 1.5 degrees above pre-industrial, and the injection rates are modified mid-simulation to try and drive the climate system towards 1.5 degrees of warming over the pre-industrial. However, we don't have the system identification necessary to design a feedback simulation for MCB yet, and so all of the MCB simulations employ a constant amount of forcing, where the percentage of the ocean surface is fixed throughout the simulation. So I will mainly be looking at one MCB simulation where the amount of cooling is closest to the SAI amount of cooling in the SAI simulations. But eventually, we hope to understand enough about how MCB impacts the climate system that we could design a feedback regulated strategy. So just as an aside, I mentioned that we'll be looking at one MCB simulation, and we're looking at one with 5% ocean coverage by surface area, because it provides the amount of cooling that's closest to the SAI simulations that we're comparing to. So these are the masks. Each month of the year, the little red shaded areas indicate the areas of the ocean which have been determined to be most susceptible to marine cloud brightening in that month. And the cloud droplet number density in those regions is artificially ramped up to 370 per cubic centimeter. I mention this because the vast majority of these for this simulation are in the Pacific Ocean. And so even though we're calling this a global strategy, a lot of the forcing is confined to one part of the globe. So that's just an interesting thing that I wanted to point out for these simulations. So getting into the results, first we're going to start by looking at the shortwave top of model flux, which is a measure of how much sunlight is actually being reflected by these simulations. So like I said, we have two different backgrounds. Our WACM simulations for and with SAI are going to be in shades of red, and our CAM simulations, which we use for MCB, are in shades of blue. So we have the SAI baseline and the MCB baseline here. So this is what the amount of forcing looks like for the SAI simulations. And you'll notice that the amount of forcing increases with time. And this is because we need to ramp up our SAI over time to maintain a constant global mean temperature. However, for MCB, we are applying a roughly constant amount of forcing. And the amount of forcing is not identical. The two simulations need different amounts of forcing to provide the same amount of cooling, but it's the same order of magnitude, 2 to 3 watts per meter squared, approximately, looking at the last 20 years of simulation. For the SAI simulation, the amount of forcing is pretty globally uniform, on the order of 2 watts per meter squared everywhere. But you might be able to guess based on the boundaries I chose for my color bar, what the MCB distribution of forcing is going to look like, because there are massive discrepancies in the spatial distribution of radiative forcing. We have forcing as low as negative 100 watts per meter squared in some grid cells. And I chose 50 to negative 50 because it was the only, if I made the scale any bigger, the arise SAI forcing wouldn't even show up on the map. But interestingly, for MCB, we also have positive forcing in some areas, which means that more sunlight is reaching the surface. And this is almost certainly due to aerosol cloud interactions and circulation changes that are actually causing more sunlight to hit the surface in some regions. So just looking at the forcing alone, we see that these two strategies are massively different, even if they provide the same amount of cooling. That distribution of cooling is also going to be different because of the discrepancy in forcing distribution. So again, we have SAI in red and pink, and we have MCB in blue and green. So you'll see that the SAI simulation with its feedback regulated injections maintains an approximately constant global mean temperature. And the amount of cooling it provides is pretty uniform everywhere, a little bit more towards the poles to offset Arctic amplification. However, for MCB, even though the globally averaged amount of cooling is the most similar to SAI of these MCB simulations over the last 20 years, we're still going to have large amounts of cooling in some areas and even some warming relative to the baseline. And we do have 10 ensemble members of each the background and the intervention. And so the shading represents areas with no statistically significant change. And we see that a lot of the changes, even the warming that we get in some regions, are statistically significant according to the two-sample t-test. So this is a brief overview of how these simulations affect the climate differently. The next thing I'm going to look at are some of the Arctic impacts, such as Arctic sea ice. The short version is that cooling anywhere on the planet is eventually, according to the laws of thermodynamics, going to provide some cooling in the Arctic, and that's going to increase the sea ice. That's going to increase the sea ice extent. The increased injection over time for SAI is going to cause an approximately constant sea ice extent over the end of the circulation. MCB, we're going to see a spike at the beginning as the cooling brings the sea ice back, but eventually the amount of forcing provided by MCB is not going to be enough to keep up with global warming, and the sea ice goes away again. This is consistent with our understanding of sea ice in climate models, because it's been shown to be very reversible. If you cool the Arctic, the sea ice comes back, and if you warm the Arctic, the sea ice goes away. And we've seen this both in historical and paleological simulations, as well as simulations of global warming and climate intervention. So over the last 20 years, the SAI simulations have more sea ice extent, but what I actually want to look at here is the sea ice extent across the different MCB simulations. So the one on the right now is 5% ocean coverage, but I'm going to put up two more. This one is at the top is 2.5% ocean coverage, and the one at the bottom is 12.5% ocean coverage. So we have less MCB at the top and more MCB at the bottom. And unsurprisingly, more MCB over a given period means more cooling of the planet, which means more cooling of the Arctic, which means that more sea ice comes back. And this is important because this is the kind of system identification that we would need to do in order to design a feedback algorithm. And while in theory, obviously increasing your MCB deployment is going to give you more of an impact, and you could design a feedback algorithm around this. This is the first time we've been able to quantify it. And so keeping this in mind, that a greater intervention means a larger response, we could theoretically use this to design a feedback algorithm in which you control the area of the ocean in which you're deploying marine cloud brightening in order to decide how much sea ice you want to bring back. I'm going to look at two more Arctic impacts really quick. The first one is permafrost. The maps that I'm showing here are a graph of the regions where the annual maximum active layer thickness, or altmax, is less than 3 meters. In short, a small active layer thickness in permafrost regions, the active layer is the topmost region of the soil, which freezes and unfreezes with the seasonal cycle. Everything below that is permafrost. And so if you have a small active layer, for example, less than 3 meters is a threshold that's commonly used in the literature, that means you have a lot of permafrost underneath. So if you're cooling high latitudes, you're going to expand the breadth and depth of the permafrost region. But again, I'm going to put up maps from different MCB simulations. We have less MCB on the left and more MCB on the right. And you'll see that the permafrost region expands as you increase your marine cloud brightening intervention. You have less recovered permafrost for the 2.5% simulation and more for the 12.5% simulation. So this is another example where we can quantify how much the response scales with the intervention. The last thing I'm going to look at is the Greenland ice sheet. So this is a map of Greenland ice sheet surface mass balance changes. So we have SAI on the left and MCB on the right. For my big Arctic case study, we found that SAI at high latitudes can increase surface mass balance of the Greenland ice sheet by reducing runoff at the edges of the glacier. Surface mass balance is the net total contribution of precipitation, evaporation, and runoff at the surface. And the green around the edges in these diagrams indicates an increase in surface mass balance because there's less runoff. So you cool the Greenland ice sheet and less of the surface ice is melting and running off into the ocean. You'll notice for the SAI figure on the left, there's a very small brown region at the bottom tip of the glacier, and that represents a decrease in precipitation. To some extent, this is expected. SAI is known to decrease precipitation because as you cool the atmosphere, you're going to have less capacity to hold water and therefore less rainfall. But what's really interesting is that MCB relative to SAI, you'll see there's less decrease in runoff and more decrease in precipitation. And both of these observations scale with the size of the intervention. So we have less marine cloud brightening on the left and more on the right. And in both cases, the amount of runoff that you have at the edges of the glacier scales, but you also see that scaling in the precipitation reduction. This is really interesting to me, and it's not clear 100% yet whether the precipitation reductions over the glacier for marine cloud brightening are due just to the reduced capacity of the atmosphere to hold water, or whether it's because of other larger circulation and cloud changes that we haven't been able to identify yet. But it's a point that I want to make is that if you have some impact of your intervention that is considered beneficial and some impact that you would consider to be negative, then both of those, the good and the bad, are going to scale with the scope of your intervention. And I think that's an important thing to point out. So in summary, the response of the climate from SAI is much more uniform than MCB, both with the forcing and the temperature. MCB does appear to preserve aspects of the Arctic climate, and these impacts scale with deployment. But this also includes other possibly unwanted things, such as changes to the hydrological cycle. This suggests that feedback-regulated marine cloud brightening is possible, where you scale the scope of your intervention based on the scope of the response you want. However, because you're changing the distribution of forcing with the scaling rather than just the magnitude, this could cause complications that we would need to work around. And then lastly, one thing I wanted to point out, I mentioned at the beginning that Arctic-focused SAI is possible because you can tailor your injection location. Because of where your marine cloud brightening is limited to based on the regions of highest susceptibility, it might not be possible to preferentially cool the Arctic with marine cloud brightening like you could do with stratospheric aerosol injection, because the regions where MCB is usually implemented are at relatively lower latitudes, and you're confined to those regions of the ocean. So this wraps up my presentation. Thank you everybody for attending, and I'd love to answer or try to answer any questions that you have about the work.
Thank you, Walker. That was excellent. Does anyone have a question? I see Alan first. Go ahead, Alan.
Hi, Walker. Very, very nice. I question your conclusion that MCB is possible. Why do you say that? The technology doesn't exist. We don't even know if we can brighten or an area. We don't know if the feedbacks have subsidence next to where you spray, and you don't even get the right sign. So I think you should really not say it's possible, say it's a proposed scheme, and if it's possible to do it, these might be the effects.
That is well said. I agree. Looking back, saying feedback regulated MCB is possible was a poor choice of words. I should have said we could do it in climate models using the scheme that Jack and Yaga used, where we artificially brighten the clouds. Given that the assumption that mechanism works, then I believe that we could wrap a feedback loop around it. But you have a very good point, which is that cloud aerosol interactions are extremely complicated, and the technology has a long way to go before we know whether we could implement it in real life. And you make an excellent point, and I agree with you.
Simone?
Yeah, thanks, Walker. Very nice. So this is interesting. You did perform some experiments like the 2%, 2.55%, and 12%, and you looked at the sea ice. And that looks like it's scaling, right? And also a slow runoff. But what if you would just look at simple quantities of temperature in other regions? Since we see that there is a warming and a cooling, is that actually linear if you look at these cases, or is it somewhat not linear because it could do different things with different greenhouse gas background conditions?
That's a good question. From what I remember from making temperature plots, it is going to scale and it's approximately, the regions are approximately similar. Like looking at the map in the upper right corner next to the slide number, if you took the same plot of temperature changes for the MCB simulation relative to the baseline in the same period, if you increase the amount of MCB, you're going to get more cooling and then also more warming in approximately the same distribution. It's not identical, and there's also going to be some variety within the ensemble members. I have not looked at that in detail. That's a good point. If you were to look at one vulnerable region that's comprised of a few grid cells, I would guess, without having looked into too much detail, that the response is going to vary a little bit in magnitude. And if you're maybe on the border of, if you look at around West 135, just south of the equator, west of South America, where there's that border between warming and cooling, I'm guessing that the location of that border is not going to be perfectly fixed, especially because you're expanding the region of where you're deploying the marine cloud brightening. That means you're changing the distribution of the forcing, and that's going to change the distribution of the cooling as well. But because the most susceptible regions are in approximately thinking about it now, I'm not sure that's correct. I think in the Pacific Ocean on the far left side of the graph, those patterns were pretty consistent. But when you introduce marine cloud brightening to other regions of the ocean that previously didn't have any in your or didn't have any in your lower scale interventions, that's gonna change a lot. I guess I'd have to spend some more time thinking about it. But yes, that goes with my third bullet point here, where I mentioned that spatially heterogeneous input and response may cause complications because you're changing the location of the forcing and not just the magnitude. If you're controlling for a localized variable, I think that's definitely gonna cause complications. Do you have any thoughts? We're straying a little bit from the things I looked at, so you might be able to guess just as well as I could.
I think it is definitely worth looking into it more and looking at different regions.
I agree.
Mike, did you have a question?
Yeah, I mean, I think this was fascinating. So the other sort of change in aerosols that's going on is of tropospheric sulfate aerosols, partly from the cleanup that's going on of marine bunker fuel, but there's some other, interesting potential looks that could be made at what happens with tropospheric aerosols, because in the past, the main salt in the sort of late 20th century, the main tropospheric sulfate focus was in the North Atlantic basin, and now it's shifted to the Southeast Asia or East Asia region or something. And I guess I'm wondering if it's worth, as sort of analog studies about how all this works, to look at at these cases of changes in sulfate of just tropospheric sulfate aerosol, about what regional patterns it's doing, what kind of effects it might be happening on the Earth, the different patterns we have, and what happens when it shifted from the Atlantic to the sort of the West Pacific region, and also whether actually doing sort of light amount of just tropospheric sulfate aerosol over the vast remote Pacific Ocean, sort of thinly spread, would actually have an interesting potential climate intervention effect.
That's a really interesting thought. I would say tropospheric aerosols are definitely not my area of expertise. And I definitely wouldn't say that I'd be better equipped to answer that question than anybody else in this call. My basic sort of understanding is that aerosols due to anthropogenic pollution are definitely masking an unknown but probably significant amount of warming. And as we clean up those aerosols, that warming is going to become unmasked, and that could possibly increase the rate of global warming. So in terms of, do we put some of those aerosols back or modify their distribution? to maybe slow the unmasking of that warming. On paper, it seems the physics are there, but yes, we would need to look at it in a lot more detail to determine whether it's a good idea or not, and what kind of impacts it would have on the climate. I'm not sure. Is there a specific question that I can have I answered your question or addressed your?
Well, in some sense, one of the suggestions about how to do climate intervention would be to do with clear sky, tropospheric aerosols. Right now, the sulfur is concentrated in particular regions where it's often populated, and so you have health effects. But if you were to spread it over the vast Pacific Ocean in much thinner concentration, you'd still have an initial effect. And it's just interesting what you say, that cooling anywhere sort of out over the ocean in these patterns actually induces such widespread, induces responses over the Earth, way up in the Arctic and stuff.
Mm-hmm. Yeah, that makes sense.
Hong Wei, did you have a question? We still have a bit of time.
Oh yeah, very quick one. Also, by the way, very great talk, Walker. So my question is, generally is like, so for the MCP simulation you use CAM. I'm just wondering, like, any source, is that possible? We can couple ocean model, just in case like their MCP may have more influence on the atmospheric ocean interactions. Any thoughts?
That's an interesting suggestion. I suppose it would be possible. That is currently would be outside the scope of my experience using CESM to set that up. But yes, I in theory you could decouple. You could decouple your different components of the model and focus on the one that you think the most important changes are in. I guess I don't feel qualified to answer whether that would be a meaningful study. It certainly sounds like a great idea. And I say, if you think you can get more information for a given amount of computer time, then let's go for it. But I don't think I understand the ocean changes well enough to recommend whether prescribing those and just looking at the atmosphere would provide the same level of usefulness.
Thank you.
Okay, perfect timing. Thank you very much, Walker, and thank you.
My pleasure.
Sorry?
Oh, thank you for having me.
Oh yeah, cool. Yeah, so yes, just wanted to tell everyone that these meetings are recorded. So you can go on the website to find recordings of the old meetings. And also, if anyone wants to give a talk in the future, you can reach out to either me or Simone, and we'd be delighted to have you on.